Welcome back to the Food Lab, everyone. I'm thrilled to be your instructor today for this explainer, because honestly, we're diving into some of the most fascinating chemistry that happens right in our own kitchens. We're talking about why our food turns brown. It's a process that literally affects almost everything we eat. From that neglected fruit sitting on your counter to the perfectly baked goods coming out of your oven. So let's unpack the exact science behind these everyday transformations, shall we?
Here's our syllabus for today's session. 1. Welcome to the Food Lab. 2. Enzymatic browning explained. 3. Non-enzymatic, caramel and Maillard. 4. Comparing the reactions. 5. Controlling the color. And 6. The final taste test. Section 1. Welcome to the Food Lab. So we've all seen this incredibly familiar problem, right? You slice a crisp apple for a quick snack. Maybe you peel a banana, and literally within minutes, the flesh develops these unsightly brown spots. Now, while it's perfectly safe to eat, it totally alters the visual appeal, and honestly, even the texture and flavor. This super common kitchen annoyance is really the perfect anchor for our study today, because what just looks like simple spoilage, well, it's actually a complex, lightning-fast chemical reaction happening right before your eyes. Section 2, Enzymatic browning explained. Okay, so the prime suspect behind this rapid browning is a naturally occurring enzyme called polyphenol oxidase, or PPO for short. Now, in an intact, totally healthy plant cell, phenolic compounds are safely locked away inside the cell's vacuoles. They're completely separated from the PPO enzyme, which is just hanging out in the cytoplasm. So as long as that plant cell is whole, they never actually meet, and the fruit stays its normal fresh color. But what happens when we disrupt that cell? Well, here's how the reaction actually triggers. When the plant tissue is damaged, whether that's from your kitchen knife slicing into it or just from getting bruised during transport, the cellular walls break down. Suddenly, the PPO mixes with those phenols. And when this happens in the presence of oxygen, PPO goes to work. It rapidly converts those phenols into highly reactive molecules called O-quinones. Then, almost instantly, these O-quinones undergo a totally spontaneous polymerization process. They essentially link together to form these large, dark, totally insoluble pigments known as melanins. It's a pretty brilliant chemical pathway, taking us from a completely colorless monophenol all the way to those complex brown polymers. Now, what's really fascinating here is the why behind all of this. The plant isn't just doing this to ruin your afternoon snack. These complex brown melanins actually form a physical barrier, and they possess real antimicrobial and antifungal properties. So it's actually an evolutionary defense mechanism designed specifically to protect the bruised plant tissue from spreading infections. Think of it like, well, it's basically nature's Band-Aid.
Section 3, Non-Enzymatic, Caramel and Maillard.
Moving on, the first major non-enzymatic reaction we need to talk about is caramelization. Now, this one is entirely dependent on sugars and high heat. By simply heating a sucrose or glucose syrup, we trigger this wild cascade of reactions. We're talking dehydration, skeletal fragmentation, and ultimately, this creates those distinct brown caramel pigments. In fact, these exact caramel colloids are heavily utilized in the food processing industry. They are literally the exact additives used to give our favorite commercial colas their signature dark brown color. Because, let's be real, they definitely aren't naturally that color.
But caramelization is really just the tip of the iceberg. Say we bake a test batch of cookies. That triggers the totally famous Maillard browning reaction. Unlike caramelization, which basically just needs sugar and heat, the Maillard reaction is a whole different beast. It requires sugars, amino acids, and heat. And on top of that, it heavily depends on some incredibly specific variables. Things like the exact temperature, the amount of water present, the pH level, and even the precise type of sugar used, like say fructose versus lactose. All of that will drastically change the darkness and the flavor of your final baked cookie. So the really crucial point to understand is this mini narrative of the Maillard pathway. As the sugar and amino acids react, they form what we call amidori compounds. Then, as these intermediate compounds degrade under the heat, they form highly reactive molecules known as deoxyazones. These guys then rapidly combine with more amino acids to trigger a truly phenomenal process called the Strecker degradation. Honestly, this specific step is pure culinary magic. It releases volatile aldehydes like methanol, right alongside compounds like hydrogen sulfide. And these volatile substances, they're exactly what give browned, roasted, and baked foods their complex, irresistible, absolutely mouthwatering aromas.
Section 4. Comparing the reactions. Okay,
To cleanly contrast these for your lab notes, just remember this one fundamental difference. Enzymatic browning is essentially a biological injury response. It's driven by the presence of oxygen, physical tissue damage, and that PPO enzyme, and it happens quite easily right at room temperature. Conversely, non-enzymatic browning is a heat-driven culinary transformation. It requires sugars, and in the case of Maillard, amino acids plus specific moisture and pH conditions. So simply put, one protects a plant while the other makes our food taste and look absolutely incredible.
Section 5. Controlling the color. So now that we know how these reactions work, how do we stop them? Well, our toolkit in the food processing industry is actually huge. If we want to stop enzymatic browning in vegetables destined for the freezer, we use a quick heat treatment, like steam blanching, to permanently destroy the PPO enzyme. If heat isn't an option, no problem. We can simply immerse the cut fruit in water or syrup to block the oxygen needed for the reaction. And for non-enzymatic Maillard browning, we can actually just lower the pH, making it more acidic. This protonates the reactive amino groups, effectively paralyzing them and stopping the browning process dead in its tracks. This brings us to one of our most effective chemical tools, sulfite inhibitors. When we add sulfur dioxide or bisulfite to a food product, it literally intercepts the Maillard reaction right in the middle. The sulfites react with an intermediate compound called HMF right near the end of the amidori decomposition. By reacting with it, the sulfite diverts the chemical into a completely stable product that physically cannot proceed to form those dark melanoid pigments. It is a remarkably precise chemical roadblock. But hey, chemistry isn't our only tool here. We also have some absolutely incredible biological alternatives to heat and sulfites. We can use what we call killer enzymes, which are naturally occurring inhibitors. For example, food scientists will use glucose oxidase to convert reactive glucose sugars into gluconic acid. That's a technique heavily used to preserve the color of dried egg whites. Similarly, we use ribose oxidase to prevent unwanted browning in fish products. We can even utilize ionizing radiation. But the overarching goal is always the exact same: carefully remove just one crucial substrate to halt the reaction entirely.
Section 6. The final taste test. Now, before we wrap up, we need to look beyond just the color and the flavor. While Maillard browning provides those exceptional aesthetics and those deep, roasted flavors we all absolutely love, we really have to recognize the nutritional cost here. Remember how amino acids actively participate in these complex reactions? Well, once they bind with sugars and transform into those flavor and color compounds, they are completely lost from a nutritional standpoint. And this is especially critical for highly reactive essential amino acids like L-lysine, which is often found in pretty low concentrations in foods like your morning breakfast cereals. Basically, the browner the cereal, the less L-lysine remains for your body to actually absorb. To finish up, I'm going to leave you with this totally unresolved question from the current scientific literature to ponder during your next highly browned meal. We know for a fact that the Strecker degradation produces those delicious volatile pyrazines. But some researchers are actively investigating whether these drastic, high-heat reactions in complex food systems might simultaneously be generating unrecognized mutagens. Honestly, the science isn't totally settled on this yet, but it's a completely fascinating area of ongoing food chemistry research. So until our next session in the food lab, keep asking questions about exactly what is on your plate.